I should start by thanking the ISHR for sponsoring this, and also for thanking Davor. We are co-conspirators in this, but actually Davor's done all the hard work, as is the way with postdocs and professors. The professors take some reflected glory, but actually all the hard work's done by the postdoc. So Davor, thank you very much. Some of you will know me out there, some of you will not. It may come as a surprise to some of you that I'm talking about dolphin diving and dysrhythmias, when actually I spend my life working on sodium and calcium regulation in cardiomyocytes. And the story I'm going to tell you today is a story about the way in which teaching and research interact. And the students tell us that our research often informs our teaching, because they know that because we give them most confusing lectures on our research subject, for sure. This is an example of where my teaching has informed my research, and I'm going to tell you a little story about that. Before I do that, I'm just going to show you a picture of where we work. This is St Thomas's Hospital. This is where the labs are here. This is where Boris Johnson currently is, our Prime Minister. He's somewhere over here. He should be somewhere over here. He's currently here. Our labs and my office look out over our CCU unit, which is over in this building here. So we're in a very nice location. That's St Thomas's. And before I really start my talk proper, I want to just say thank you to all my clinical colleagues in the NHS who are doing an unbelievably good job at the moment. I'm very proud of the NHS, so I've put a little thank you up here. But I know around the world, our healthcare partners all around the world are just doing an amazingly good job. So thank you to all of them. As I say, this is a story about, that starts at least in teaching. And I run a course, a third-year course for our undergraduates called Extreme Physiology. And Extreme Physiology, as you can guess, looks at the physiology of various environmental extremes: spaceflight, aviation, G-forces, altitude, things like that, diving, hypothermia, hyperthermia. And I really love teaching this course. It's great fun. I get some really amazing lecturers to come and teach on this course. And one of those amazing lecturers is this guy. This is Mike Tipton. Some of you will know Mike. Mike is Professor of Human and Applied Physiology at Portsmouth University. He's editor-in-chief of experimental physiology, and his real expertise is in sea survivals, survival in cold water. And Mike has taught on my course now for, well, nearly 20 years, I think. And there are some amazing statistics that I learned from Mike. Here's some statistics about drowning. Approximately 400,000 immersion-related deaths per year. That's one pretty much every minute, give or take a bit. It's the second most common cause of accidental death in children and the third most common cause of death in adults. Now here's the weird stuff. 65% of drownings involve strong swimmers. Well, that maybe is no great surprise until you hear the next statistic, which is 60% of those are within 3 meters of a safe haven. Why is it that we cannot swim for 3 meters to save our lives? It's very weird, okay? So there's something weird going on here. And here's something that I spotted in one of these free newspapers we get on the subway or on the tube trains in London. I picked this up in 2005 when heading over to Guy's Hospital, where we do most of our teaching. And I was on my way to listen to Mike Tipton talk. And this is the story of a guy called Andrew Funnell, who was a young, fit, healthy guy who died falling off his windsurfer into cold water. And as it says here, and the Metro newspaper is not known as a high-ranking physiology journal, but they've done a decent job here. He suffered a form of cardiac arrest called vagal inhibition, caused by sudden exposure to cold water. Mr. Funnell, who was wearing only shorts, probably died almost instantly. So there's a thing. What is it about falling into cold water that is so amazingly dangerous? And it's not just windsurfers. The US triathlon authorities realized that there was a disproportionate number of deaths during triathletes, or amongst triathletes. 43 deaths in that period you see there. 79% of those occurred in the swim phase. And as Mike Tipton put it, these data suggest that the swim represents the greatest relative hazard associated with mass participation sports events. And the available data indicates that the swimming fatalities appeared to be caused by episodes of sudden cardiac death. So there's something about going into cold water and taking exercise at the same time, which is inherently dangerous. And it really comes as no surprise to us. Here's some pictures that Mike supplied me with, that going into cold water is dangerous. I won't repeat all of Mike's jokes, but one is worth repeating, which is, he points out that you know your experiment is dangerous when you replace your laboratory safety officer with a priest. So these are some of the pictures from Mike of the hazards of cold water immersion. So what I'm going to do in this talk today in the next 30 minutes is talk to you about the cardiovascular responses to immersion. I'm going to talk to you about specifically the ECG changes that happen during the diving response when your face gets cold and wet, and I'll talk a little bit more about that in detail. And I'm going to introduce you to the concept of what we've called autonomic conflict, where the autonomic nervous system is the two limbs of the autonomic conflict are in a conflict with each other. And finally talk about the sort of blindingly obvious is what are predisposing factors that take an inherently safe thing like going into water and make this dangerous. So we'll start off by thinking about the cardiovascular responses to immersion. And there are two really main reflex responses that occur, the cold shock response and the diving response. And we need to think about both of those. The cold shock response is the blindingly obvious one. You go into cold water and you take a big gasp. You take a real deep breath. There's a gasp reflex, which is uncontrollable. You get an increase in heart rate, tachycardia, and you get a hyperventilation. That hyperventilation, of course, is dangerous if your airway is becoming submerged. So the cold shock response is an irresistible urge to breathe, a gasp, and a tachycardia. So this is predominantly driven by the sympathetic nervous system. On the other hand, many of you will know about the diving response, which is activated when just our face gets cold and wet. And here's some students doing a diving response practical as part of the extreme physiology course. Now, the diving response features an apnea, a breath hold. You can hold your breath longer when your face is cold and wet. A decrease in heart rate and a decrease in peripheral blood flow with an increased peripheral vasoconstriction. And the breath hold, and the decrease in heart rate are vagally mediated and driven by the parasympathetic limb of the autonomic nervous system. So we've got two different responses here, depending on whether just your body gets cold and wet, or indeed your face gets cold and wet. One of them presses the accelerator and speeds your heart up. One of them presses the brake and slows your heart down. And so the question is, what happens if you activate these two responses very hard at the same time? You push the accelerator very hard, you push the brake very hard. Well, this analogy isn't perfect, but it's amusing, so I'll show it to you anyway. Have a look at this. Don't try this at home, by the way. This is David Coulter doing donuts on the roof of a tower in the Middle East. As I say, not to be recommended, but pushing the brake very hard and pushing the accelerator very hard at the same time, and not wishing to stretch the analogy too far, may induce the sort of arrhythmias you see in the top right-hand corner of the slide. Indeed, it does induce arrhythmias. And one of the first slides that I saw when Mike Tipton started talking to my students 18 years ago was this one here. And this is the ECG from a fit, healthy Portsmouth student immersed in cold water. And what you see in about 35% of students, I assume they're a normal population, is this strange arrhythmia or dysrhythmia where we get a bradycardia interspersed with periods of tachycardia. So bradycardia, tachycardia, bradycardia, tachycardia. So if you see the heart rates 55, 127, 53, 162, a PVC here, 140, 61, 155. These bursts of tachycardia interspersed with bursts of bradycardia. And this is very common and idiosyncratic. You take the same person 2 weeks later, do it again to them, they will do exactly the same thing. If we put people into cold water alone with the head out with breathing, we see this arrhythmia very rarely. If you put people in with a breath hold, so it's cold shock plus breath hold, 63% of people will show this type of behavior. And if you combine cold shock with facial immersion, 80% of normal, fit, healthy young people will show this type of tachycardia, bradycardia, tachycardia, bradycardia type rhythm. So a very unusual rhythm. So the question is this dangerous? Well, presumably not, because we all go into cold water a lot of the time. But maybe it is dangerous if we have other predisposing factors. So channelopathies, mutations in ion channels, atherosclerosis, it's what your grandmother would tell you. If you've got heart disease, don't go jumping into a freezing cold swimming pool. Cardiac hypertrophy, of course, gives more room for re-entry type arrhythmias, and so having a big heart is a predisposing factor to serious arrhythmias. And of course, drugs, whether they be recreational, performance-enhancing, or medicinal, therapeutic drugs, drugs can influence our susceptibility to arrhythmias. Indeed, I just read something today saying that some of the treatments for COVID-19 may prolong QT intervals, so we need to be cautious. So what happens to the ECG when we activate this diving response or diving reflex? And the first thing we thought about was to look at the QT interval, because that is a real predictor of what happens in terms of arrhythmia susceptibility. So thinking about the QT interval, the first time we did this practical with our students, here was an example that the students recorded of their heart rate during a facial immersion. Here the heart rate is about 100, 110 going into the facial immersion. Students are a little bit excited, a little bit stressed, the heart rate's a little bit high. Facial immersion here for about 30 seconds, lowers their heart rate down to, in this case, about 45, 50 beats a minute, okay, within 30 seconds. So we've got a big change in heart rate, and the question we asked our students very early on was, what happens to the QT interval? You all know that as the heart rate slows, we should get a prolongation of the QT interval, of the action potential duration. So the students went away, this is some of their data from the first practical, and they measured the QT interval on a control heart rate, in this case at baseline of 110, and during a diving response, in this case at 58 beats a minute. You can tell this is a student practical because the ECGs are all noisy and horrible. But nonetheless, this was the first practical we did. Here was the mean change in heart rate, and here were the effects on the QT interval. And what you can see is that although the heart rate goes down by about 50% to about half, the QT interval really doesn't change at all. So despite this profound bradycardia, no change in QT interval over the duration of this facial immersion. So we did some more studies, again a student project here in the lab at St Thomas's, looking at the relationship between heart rate here and QT interval on the y-axis here. These are steady state measurements made from a sitting position, lying down when your heart rate slows down. Light exercise, heart rate speeding up, and moderate exercise, heart rate even faster. The heart rate here expressed as RR intervals, so these are fast heart rates, these are slow heart rates at this end. And this is what happens when you activate a diving response from a sitting position. Putting the face in water slows your heart rate down profoundly, but does not change the QT interval at all. Okay, so there's no change in QT interval, despite a profound change in heart rate. We might expect this to be somewhere up on this line, somewhere around here. So what are the implications of that? Well, the implications are that if you've got a short action potential or a narrow QT interval, you've got a reduced relative refractory period. You've got a bigger gap in the diastolic interval to have more arrhythmias. So you have an increased susceptibility to arrhythmias if the QT interval does not fill the diastolic interval. So we asked ourselves, why don't we see a change in the QT interval during the diving response? And one obvious possibility was that the heart rate changes are simply too fast. The QT interval can't keep up. And if we waited longer, we would be able to see the QT interval catching up. There's a latency in this QT response. So what happens if we prolong the breath hold facial immersion for longer than 30 seconds? Well, this is easy to say and harder to do. Some of our students found it difficult to hold their breath for 30 seconds, let alone longer than 30 seconds. So we decided we needed to recruit some breath hold divers. We would have loved to have recruited some of these, but unfortunately our animal unit was not having any of it. So we recruited some of these, okay? We recruited some breath hold divers, and amazingly, there are at least 7 free dive clubs in central London. Seems a strange place to go diving, but anyhow. And we recruited 7 trained breath hold divers from London Free Dive Clubs. We asked them to have a minimum breath hold dive duration of 4 minutes. And we brought them into the lab and we measured ECG changes during a 3-minute facial immersion. We chose 3 minutes because they said they could do 4, and we figured, they'll do 3 easily. So we then compared this to recovery from exercise, like I've shown you before. And here's the data, very much like the student data. That is, here's the relationship between heart rate and QT interval under steady state conditions. Here's what happens in the free divers who could breath hold at 30 seconds. In fact, in their case, their heart rate fell quite profoundly and the QT interval actually decreased slightly. But what happened when we then took them out for longer? When we got to 3 minutes, the heart rate fell even more, but the QT interval started to rise. So there is a latency in this response, but it never gets back up to where it should be, perhaps, on the steady state line here. So something is holding and preventing the QT interval from prolonging. Here's these data shown in a slightly different way, normalized to the starting heart rate. So here's where we start at the start of the diving response. And here's what happens to heart rate on the x-axis and QT interval on the y-axis here. And the numbers next to the points here are times. So at 10 seconds, we're here, 20 seconds, 30 seconds, 40 seconds, 50 seconds. After a minute, QT interval starts to prolong. Here's 70 seconds, 80 seconds, 90 seconds, etc. So you can see that for the first minute, the QT interval is kept short and then starts to prolong out after in minutes 2 and minutes 3. And if you just compare that with the recovery from exercise, when we've been exercising and our heart rate starts to fall after exercise, you can see that the recovery from exercise is more linear and doesn't show that sort of lag phase. So we came to the conclusion that something is keeping the action potential short during this first minute. And one possibility is that the diving response not only involves a bradycardia, but it also involves sympathetic activation and a peripheral vasoconstriction. And that sympathetic activation could be preventing the action potential from prolonging. We know that sympathetic agonists will activate currents like IKS in the ventricular myocardium, and that will tend to shorten or keep the action potential from prolonging. So that brings me on to this idea that we've got 2 different limbs of the autonomic nervous system, both contributing to what we're looking at here. We've got the sympathetic and the parasympathetic limbs of the autonomic nervous system. And the idea is that perhaps we know that the sinoatrial node and the atrioventricular node are particularly well innervated by the autonomic nervous system. Sympathetic nerves to the sinus node and parasympathetic nerves can control heart rate. But the ventricle itself is not so well innervated with the parasympathetic innervation, but is very well innervated with sympathetics. So when we have sympathetic activation, we're going to have effects both on the ventricle and on the sinus node and on heart rate. And when we have parasympathetic activation, it's going to predominantly affect the nodes, the sinus node and the AV node. So is this sympathetic activation of the ventricle antagonizing the effects of slowing heart rate? Is the question we wanted to know the answer to. Well, we can get a little bit of information by looking at heart rate variability in our breath hold divers. The high frequency component of heart rate variability is thought to reflect parasympathetic activation, whilst the low frequency component is thought to reflect sympathetic activation. So we see as we prolong the breath hold and facial immersion here, we get an increasingly strong parasympathetic drive to the heart, which is making the heart rate slow down. The sympathetic drive to the heart starts high in the first minute, but falls in minutes 2 and minutes 3. In fact, if we look at the ratio of the high frequency to low frequency ratio here, which is an index of sympathetic dominance, we see that the sympathetics dominate in that first minute, but then wane later in minutes 2 and 3. And we can ignore the very low frequency component because that's simply the fall in heart rate. So we then wondered, well, 3 minutes is all well and good, but what about real diving animals? These guys who can dive for a long time. What happens to their heart rate? What happens to their Q interval? Do they show this QT hysteresis? And do they even have arrhythmias when they dive? Do they have these bouts of tachycardia and bradycardia? And as they say, an hour in the library is worth a month in the lab. So we went to the library, and I found this wonderful paper by this guy, Russ Andrews, who took these elephant seals, and there's a good story here, and he telemetered these elephant seals. And these elephant seals like to live on a beach here in Northern California, just north of Santa Cruz. And they picked these elephant seals up off the beach, put them in the back of a truck, drove them down Highway 1 to Monterey Bay here, put them back in the water. You've now got a very annoyed elephant seal, and they swim back to their home beach, and in doing so, cross this Monterey submarine canyon. And this is a very deep, it's over a mile deep, just in this place very close to shore. So these elephant seals come over this, and when they come over the canyon, they dive. They can't resist it, and they dive. Some of them go as deep as 1,600 meters. Most of these guys went to about 400 meters. And here's the ECG that Russ Andrews very happily included in his paper. And so with a magnifying glass, I went through this and measured up all the QT intervals from this elephant seal during a dive. And here's what I found. A pattern that looks remarkably similar to the one that we'd seen in the diving response in humans. That is a profound slowing of heart rate with no prolongation of the QT interval, followed by the QT interval tracking out. So it does appear that these guys behave, at least in terms of their QT interval, a little bit like the humans. But we wanted to do some measurements ourselves, so I contacted this lady, Terry Williams. Terry runs the Marine Mammal Center at the University of California in Santa Cruz, and she is the lucky owner of Primo and another dolphin who were trained by the US Navy to dive sort of on command. So here's Primo having a neoprene jacket put on, which contains an ECG telemetry device here. And with Sean Loren's help, we did some measurements of ECGs on these dolphins. Here's a little video showing a dolphin dive off the coast of California. And I want to just draw your attention to how much effort this guy's putting in. Okay, he's gliding around here now, just looking around, having a nice time, not putting much effort in. But when they see a fish, they really go for it because they're trying to catch this fish. Here they are, high stroke frequency, putting a lot of effort in, and then they intersperse that with periods of gliding. He'll just glide around back up to the surface. Okay, and the relevance of this you'll see in a second, because when we're thinking about the diving response in humans, we can easily imagine what a cold shock response looks like. We go into cold water and we take a gasp and we're stressed, there's a tachycardia. But when you think about a dolphin or indeed a seal or any other diving mammal going into cold water, do you think they have a cold shock response? Does that seal rolling into the Arctic Ocean off an ice floe, does it really go, oh, that's cold? I doubt it. You know, these seals and these dolphins, this is their world. They don't roll in and they don't get this cold shock response when they go into water. But they do get a very strong diving response. So, what in humans, we get the diving response, but in diving mammals, of course, they exercise, as I've just shown you. They put in little bursts of exercise, which will activate sympathetic drive, will activate tachycardia, or at least will increase their heart rate over and above that prevailing in a diving response. So can exercise really stand in for and substitute for the cold shock response in these diving mammals? Here's some ECG data from Primo. This is showing that we get just that same sort of pattern of ECGs that we saw in humans. That is, little runs of faster heart rates interspersed with runs of slower heart rates. So here, 33, 19, 36, 15. This isn't a tachycardia per se, but it's certainly an increase in heart rate. The resting heart rate in a dolphin, somewhere around 120, 100, 120, something like that. So this isn't a tachycardia, but it is an increase in heart rate interspersed with decreases in heart rates in very much the same sort of way. What happens if we press the accelerator, if we increase the sympathetic drive? Well, we can do that by looking at the relationship between how much they're exercising here and how many arrhythmias, or dysrhythmias as we should call these, I guess, we saw. And you can see there's a very nice bell-shaped relationship where the harder they work, the more they press the accelerator, the more we see these patterns of tachycardia, bradycardia, tachycardia, bradycardia. When they work really hard, the tachycardia just dominates. Similarly, if we press the brake a little bit harder with these dolphins, the deeper they dive, the stronger their diving response they get, the lower the heart rate they get. So as they dive deeper and deeper and deeper, they get a stronger diving response. They press the brake a little harder, they get a more profound bradycardia. And you can see again, if you press the brake very hard, we get this nice relationship between parasympathetic drive and the number of these and pattern of these tachycardia, bradycardia incidents. So the idea we came up with was that the two limbs of the autonomic nervous system antagonize each other, not just in diving dolphins, but also in man when we fall into cold water. We get periods of the accelerator dominating, periods where the brake dominates, tachycardia, bradycardia, tachycardia, bradycardia. And these all occur with the simultaneously pro-arrhythmic failure of the QT interval to adjust to the underlying rate. The QT interval doesn't adjust, and yet we're getting periods of tachycardia, bradycardia, tachycardia, bradycardia. So that led us to introduce this concept that Mike Tipton and I named now a few years ago of autonomic conflict, which, as I say, we think is benign in 99.999% of the time, but may cause arrhythmias when we have predisposing factors. And here's some of the possible predisposing factors that may contribute. So we decided to look at this in the lab, looking at isolated heart models of arrhythmias. And the first model we looked at was one where we substituted innervation for agonists. So we perfused a heart, this is a rat heart, perfused with adrenaline and noradrenaline, and interspersed with periods of acetylcholine to simulate parasympathetic drive. And here's the first ECG we ever recorded doing this. Here's the whole run of the ECG. Here's some examples from different points in this trace. A tachycardia here at the start because it's in adrenaline. We then see some escape beats during acetylcholine. We see some AV block. And we see this arrhythmia here, which is torsade de pointe, which is very unusual to see in an isolated heart preparation. So we were very excited. Autonomic conflict-induced arrhythmias. The problem is that we then spent the next 2 years trying to reproduce that very first experiment, and we could not reproduce it, okay? And as a slight tongue-in-cheek statement, never repeat a good experiment, as it says there. We could not reproduce it. So apologies to Andras Farkas, who was the poor guy who spent 2 years in the lab trying to reproduce it. Andras is now probably on the front line in Hungary treating COVID. So Andras, if you're listening, Apologies and good luck. So what's the explanation of that? Why the neurotransmitters, global application of neurotransmitters, not mimic the heterogeneity of neural input? Well, we decided we'd set up a model of neural innervation in the heart to try and see if we could get more information about this. This is a rabbit heart model that is isolated with the intact vagal nerves coming into the heart and the cardiac nerves, the sympathetic nerves, also innervating the heart, so that we could stimulate both vagus and sympathetic inputs to the heart. When we used this model, we saw that the relationship between heart rate and QT interval is indeed shifted by sympathetic activation, in this case with catecholamines. You can see that it shifts this relationship downwards, such that if you're at this point on a control line, you slow the heart rate down, but then also add a catecholamine at the same time here, you can come back to the same QT interval level as you started from. And that's just shown graphically here. Vagal nerve stimulation prolongs the QT interval, but if we combine it with sympathetic stimulation via catecholamine exposure, we see that's antagonized. We looked for a pro-arrhythmic effect of this autonomic conflict, and we found that we virtually didn't see one. Disappointingly, the combination of these two stimuli really didn't do very much. Vagal nerve stimulation increased the number of PVBs, but combined with catecholamines, didn't really make it much worse. Salvos, again, we got more salvos with vagal nerve stimulation, but again in catecholamines, was not really exacerbated, nor was incidence of ventricular tachycardia. So disappointingly, we had no evidence to back up our hypothesis. So that leaves us with some possible explanations. Possibly the model is wrong, possibly the conditions are wrong, possibly we're just plain wrong, the hypothesis is wrong, or possibly predisposing factors are necessary. So what predisposing factors should we factor into this type of experiment? Well, we've listed these before: channelopathies, atherosclerosis, etc. And one of the ones I want to just pick up on in passing is this one, is drugs, okay? This is off a website. Gordon Benson is a top UK triathlete. This is information on his website about how to be a good triathlete. And caffeine is king, according to Gordon Benson. An hour before a triathlon, I drink a can of Red Bull and I take a caffeine gel. I have more whilst I'm on the bike, which comes after the swim and before the run. Okay, caffeine, a lot of caffeine. In fact, if you calculate how much caffeine some of these guys, their plasma caffeine can go up to 200 or 300 micromolar. And for those of you who do arrhythmia analysis or cell work, will take a sharp intake of breath at that point. Is it dangerous? For sure it's dangerous. Have a look at this. Here's an example. Teenager died after she knocked back 10 Jaeger bombs, okay? Combination of Red Bull and alcohol, lots of it. Interesting, she died on her bathroom floor. In fact, she was taking a shower. Comes back to, is cold water, or at least water on the face, a trigger for arrhythmias? And it seriously doesn't help if you've just drunk 10 Jaeger bombs. Alcohol mixed with energy drinks, arrhythmias, Red Bull causing arrhythmias, energy drinks and atrial fibrillation. Lots of stuff in the literature about this. What else might be dangerous? Well, I've gone on for too long now, but I'll just finish off. Hopefully you'll bear with me. Channelopathies, okay. Long QT syndrome is a syndrome of ion channel mutations. It's a genetic abnormality where carriers are characterized by having a prolonged QT interval of the ECG. It gives us a massively increased risk of sudden death, and it occurs pretty frequently, 1 in 5,000 people. The diagnosis is obviously based on the ECG, but it also associates with unexplained syncope, fainting, family history of congenital neural deafness, etc. So all sorts of ion channel problems here. And there are two types of basic channel mutations that we need to think about. There's gain of function mutations of the sodium channel, long QT3. This is a mutation in which the arrhythmia is exacerbated by slowing of the heart rate, and treatment is a pacemaker. And the other type of long QT mutations are those of loss of function of potassium channels. So LQT1, 2, 5, 6, 7, etc., exacerbated by tachycardia, and the treatment is a beta blocker. Do they associate with swimming? Yes, for sure they do. So here's again a lot of papers. Swimming, a gene-specific arrhythmogenic trigger for inherited long QT syndrome. Lots of papers saying there's this association between immersion and sudden death. And here's a really nice example. This is a little girl, 12-year-old girl, pre-diagnosed with long QT syndrome, already has an implantable cardiac defibrillator. And I'll read this to you if you can't read it on your screen. She's swimming in the Pacific Ocean. After diving headfirst into the water, she immediately reported feeling very weak and then became syncopal. Her 14-year-old brother standing next to her pulled her up out of the water after several seconds and reported feeling a single forceful jolt or contraction. The patient then immediately regained consciousness and was found to have normal perfusion by the local lifeguards. Subsequent interrogation of the ICD demonstrated the sequence of cardiac events that corresponded to the clinical events. The entire sequence from sinus rhythm to cardiovascular collapse and countershock to restore sinus rhythm was less than 20 seconds. And here's her ECG. Not very good quality, and there are two types of ECG here, what's called the bipolar ECG or the far field ECG, which is more akin to what you would record on the surface of a patient. Here she is standing next to the water. She's got a sinus tachycardia. She's excited. She's about to go swimming with her brother. At this point here, she dives in. We get a PVC. We get another PVC here, a variety of weird shaped complexes. We get a long pause here, a brady-cardia, a PVC here, and then this arrhythmia here, which I've labeled as polymorphic ventricular tachycardia, or indeed maybe even torsade de pointes. Weirdly, the people who read this paper label this as VF. I don't think this is VF. You can all butt in and correct me if you like. She's countershocked at this point, goes back into sinus rhythm. So she's got periods of tachycardia, bradycardia, PVCs, and a serious arrhythmia, which would have killed her if she hadn't got a defibrillator. So syndrome in the lab using our isolated hearts. Well, we took our innovative rabbit heart, we perfused it with clofilium, which blocks IK and prolongs the QT interval. And we looked at two conditions, a combination of ventricular nerve stimulation with steady state adrenaline or noradrenaline and bolus noradrenaline. Okay, and this is showing that we can prolong the QT interval. This is at different heart rates. This is stimulation frequency of the vagus nerve. So as the heart rate slows down with increased stimulation, we get a prolongation of the QT interval, and that occurs at all heart rates. When we've got clofilium on board, we get a prolongation of the QT interval. When we did this under steady state adrenaline or noradrenaline, we found that that actually reduces the number of arrhythmias that we get, both in terms of EADs, VT, and a combined arrhythmia score. But if we actually put a bolus of noradrenaline on, rather than as a sudden, sharp, sympathetic drive, essentially, that profoundly exacerbated the arrhythmias, and we got some complex arrhythmias. We had increases in VT and VF when we combined vagal nerve stimulation and bolus noradrenaline. So we think this autonomic conflict is a real cause of arrhythmias in people who are susceptible. People who have channelopathies, have atherosclerosis, have long QT syndrome, etc. And before I finish, I just wanted to raise the possibility that this is not just unique to cold water immersion. We get people who suddenly have serious arrhythmias when their alarm clock goes off in the morning. That's called alarm clock syndrome. And here's an example of an ECG where an alarm clock's gone off at 7 a.m., the patient already instrumented, and they went into ventricular fibrillation. So when we've got strong parasympathetic drive and then a sudden shock, this can be dangerous. We know that there's a circadian rhythm in sudden death. And that circadian variation may be related to the circadian variation in the parasympathetic drive to the heart. And we know that other conditions, environmental conditions, can trigger dangerous arrhythmias. Shoveling snow is a good example. We don't get much of it in London, but any of you in Canada or somewhere like that will be familiar with all people of my age going out and doing more exercise than they should whilst shoveling snow. Loads of papers on sudden death associated with snow shoveling. So in summary, what I've told you is that cold water immersion is associated with a disproportionate number of sudden deaths. I've told you that it activates two profound reflexes. One is sympathetically driven and one is parasympathetically driven. I've told you that that generates a condition that we've termed autonomic conflict, which alternates tachycardia, bradycardia, tachycardia, and bradycardia. And these pro-arrhythmic stimuli occur at a time when the QT interval does not match the prevailing heart rate. I've shown you that similar types of dysrhythmias occur in diving mammals when diving at depth. And I've shown you that these type of inputs to the heart are insufficient alone to induce serious arrhythmias. They'll only induce, and that makes sense. We all go into cold water and most of us don't die. So they only are dangerous when we have other predisposing factors, long QT syndrome being perhaps one of the most important. And the final conclusion of this is think very carefully about how you dive into the sea next time you go swimming. So thank you for your attention. Before I finish, I should just thank a few people. Mike Tipton, of course, who started this whole thing, Avijit Datta, who made some of the early ECG recordings, and Jim House in Portsmouth, Terry Williams and Sean Loren at University of Santa Cruz, California and Santa Cruz, Andres Fahlman, who's a collaborator on a lot of the mammalian diving mammal work, and my colleagues at King's, James Clark, Andras Farkas, who's now back in Hungary, and Mike Curtis, James Winter, who did the isolated heart work, and Darren Griffiths, Sam Wong, and Eleni Nikolopoulou, who were the students who got involved in the ECG analysis. Thank you, everybody, for your attention, and I apologise for, as always, taking too long. Thank you. And I will give my screen back to Davor, if I can.
Yes, you can stop sharing now if you like.
I have stopped sharing.
Perfect. Right, well, thank you. That was really phenomenal. I mean, I've heard some of it. There are new parts that I haven't heard, so really, really nice talk. So there's lots of questions.
Okie dokie.
So if you'd like to start.
Okay, so I've got a lot, works perfectly. Perfect, thank you. I'll just stop at the perfect thing. Yeah, I think that'll do. Okay, I'm going down both videos.
Yeah, there's been a bit of an exchange.
Okay, right. Okay, so we've got our first sensible question from Ben. Oh, Ben Levine. Hi, Ben. I think there is more likely to be kicking in the face, aspiration of a small amount of water, and then drowning. We're talking about the first 200 meters of the triathletes. And Ben raises absolutely perfect point here. This is absolutely the problem, is that most of the deaths in triathletes appear to occur in the first 200 meters. And if you saw that picture I showed, the water is churning. It's like a washing machine. There's people jostling for position, people going really hard at it. For sure, that is a major factor, is aspiration of cold water, being kicked in the face, etc. You know, it is but the sympathetic drive that accompanies that stress is also there. And what you don't see is these guys dying in training. So I think Ben's quite right that the stress of the competitive nature, the washing machine environment they find themselves in, is a real factor that feeds into this. So yeah, absolutely, Ben, I completely agree. And greetings from London. Rich Head has a question, but I don't think he's said what it is. Rich Heads has. I can't see any more questions after Richard Heads, Davor. Can you?
Can you not?
No, I can.
Why that is? So there's lots of questions.
So would you like to read the question out to me? I'm at the bottom. Scroll to the bottom of my list of questions.
Okay. So I mean, I'll first go for. Let me go to the top. So
okay.
Alicia has noticed that there is an answer actually in the. She was asking about what temperature do you need for the experiments for facial immersion, but then she's realized that you showed the answer in the next slide.
Well, no, I didn't really, because the answer I put up on the screen is not the ideal answer.
Okay.
I think on the screen it's 4 to 8 degrees or something on the screen, but the reality is that's a bit cold. Okay, if you want to do a nice diving response type experiment, the ideal temperature is around 12, 13 degrees centigrade. The problem with going too cold is it hurts. So you get that sort of ice cream headache when you stick your head into really cold water. And if it hurts, then you get a greater sympathetic drive, which tends to overdrive the parasympathetic drive. So I think the answer is around about 12 degrees. We were a bit cold on some of those experiments I showed you, first of all. I've actually just realised, well, there's a load of questions in the question and answer.
Yes, that's
I was looking at the chat. Okay, so I've now just found
yes.
the correct questions. Right, so Heather Gunn. Have long-term studies been conducted to investigate the effect of cold water shock over time, not just in the first few minutes? Does cold water shock have any long-term cardiac effects in healthy people? I guess it depends what you mean by long-term here, but I'm thinking you're not thinking months here. I'm thinking you're thinking minutes to hours. So the cold shock is very much an immediate response. Okay, so you have that gasp. If you habituate to that cold water, your respiration can come under control. So, yeah, and will come under control. So the secret of, I shouldn't be talking about this, Mike Tipton should be talking about it, but the secret of survival is get through those first few seconds, okay? So that cold shock response is a very acute effect. The longer term cardiovascular effects, I wouldn't term them cold shock response, but of course they are hypothermia related, they're hypovolemia related. So the longer you spend in water, the more hydrostatic effects you have on your blood. For example, pushing blood into your thorax, causing a diuresis, causing you to become hypovolemic. The cold is associated, of course, with peripheral vasoconstriction, hypothermia, loss of muscle strength, and eventually, when you get seriously cold, seriously hypothermic, of course, that has direct effects on the heart as well. So short term, the cold shock response tends to be something that we refer to as an acute event happening within the first couple of minutes of going into cold water, but thereafter you have immersion related and hypothermia related cardiovascular events, which are separate but no less dangerous. So next question, I'm hoping that's answered the question. I mean, coming back to Heather's question, of course, those are the things, swim failure and drowning, of course, is massively important. But if you've got a life jacket and a good life jacket, then the question is what happens in the longer term if you can continue to breathe. Daniel Johnson says, is there any info on left ventricular pressure in diving models? Is it possible that mechanical factors are also contributing to arrhythmogenesis in this situation? I think we need to, when we're talking diving models, I'm thinking you're thinking people, not seals and dolphins. There's quite a lot of interesting work been done on seals and dolphins, but the hydrostatic compression is really important, and your position in the water column becomes relevant. So if you're head down in the water column, your hydrostatic load is different to if you're head up in the water column. So people diving, definitely there are if you just think the average person is taller than me, so 1.8 meters or something like that. I don't know, I don't work in meters. The hydrostatic difference between your head and your feet when you're vertical in the water column is quite significant. So if you're vertical and upright, head at the top, the pressure on your feet is tending to push blood back into your chest, and that can be as much as 600 mils of blood will move from your compressible veins in your legs back up into your thorax. That has a big impact on your cardiac output initially. That effect on your cardiac output then has an effect on your kidneys, induces a diuresis, etc. If you're head down in the water column, you get the opposite hydrostatic effect. So yes, the answer is big effects of hydrostatic effects. Crystal, hi Crystal. Crystal Ripplinger, have you done experiments with the divers where they just hold their breath for 3 minutes without facial immersion? No, we haven't actually. If you look at the diving response, and apnea is a sort of different question, but if you just look at the bradycardia that you get from apnea alone versus a facial immersion in combination with apnea, the strongest signal by a long way is the facial immersion, and the facial immersion in cold water. If you use warm water, the signal's less good. If you just do a breath hold, you still will get a slight bradycardia, but it's quite small. Okay, so we didn't specifically look at that, Crystal, but it still does have clearly an autonomic effect. And in fact, the biggest incidence of those type of tachycardia, bradycardia arrhythmias that Mike Tipton sees is actually at the break of breath hold. Okay, it's not during the breath hold, it's at the break of breath hold. That's very often where you see the highest frequency of these arrhythmias occurring. And we think that that's where you get the strongest parasympathetic drive, is just at that second that you break your breath hold. So break of breath hold is particularly important rather than breath hold per se, but we didn't look at it. Ben Levine, again, I would argue that HRV is, yes, I agree. HRV is not a good measure of autonomic activity during breath hold. I agree, Ben. It was all we had. I had the pleasure of sitting in on a talk you gave in London a couple of months ago, and I was very jealous to see the measurements you made of autonomic activity. And so if I could come to Texas and do some experiments with you, I would love to, because I completely agree. HRV, not only is it not a good measure, but it's the only one we had, but also 1 minute of measurement is not statistically very useful, I agree, for HRV. It's all we had, and so we did our best. But if you're inviting me out to Texas, I'd love to come.
When is your next sabbatical, Mike?
Well, as soon as I'm out of lockdown, I shall be off to Texas. Rudo Fishmeister, hi Rudo. Did you measure ECG parameters and heart rate during recovery from facial? Yes and no. Yes, we've recorded them, and no, we've not measured any variables from them. We've got the records, we can go back and look at it. We haven't specifically done that. Casey Park, who's he? Hi, Ben. Hi, Ben from Texas. So he's talking to Ben. He's not even bothered with me. Out of curiosity, why do you believe age? I think we've answered that one, Casey. Otherwise, email me afterwards and I'll explain. Ben, again, another question. Steve Hull and Ernesto Vanoli demonstrated a long time ago in dogs who reproducibly develop VF that a coronary occluded during exercise, that stimulation of the vagus nerve completely prevents VF virtually 100% of the time. Yeah, I think that's the whole concept of vagal stimulation and its effects on the heart is really amazingly interesting. I don't think we ever would argue that vagal stimulation per se is what's the problem here. It's the problem, we believe, is the antagonism between vagal stim and sympathetic stimulation. So yeah, I completely agree. Emma Robinson, interesting to see heart rate variability with what happens to QTC, beat to beat variability on facial immersion. Well, the QTC question, of course, is the one that we set our students in the first place, is that we said to them, okay, go away, measure the fall in heart rate, measure the QT prolongation. And we said to our students, the QT interval will prolong, and we want you to plot a graph showing QTC. Okay. And they all went away. And then about 4 or 5 days later, they started emailing me and said, but Professor Shattock, the QT interval doesn't change. So I just assumed, being students, that they'd just done it wrong. And I said, of course it changes, go away and measure it up again. And they came back and they said, no, it doesn't change, Professor Shattock. So I went away and looked at the data, and sure enough, it doesn't change. So because the QT interval doesn't change, you can't correct something that doesn't change. You can't correct the QT interval for something that hasn't happened. Okay, so what actually happens if you use a Bazit's or some similar sort of correction is, because the QTC has not changed, you then get an artifactually wrong calculated QTC, because you've corrected something that didn't need correcting. Okay, so yes, we did measure QTC under those conditions, but you're fixing something that ain't broke. If the QT interval hasn't changed, you don't have to correct it for heart rate. So Peter Penson, can the cold shock response be employed therapeutic in emergency situations which might want to administer catecholamines, anaphylaxis, resuscitation? Well, of course, the cold shock, I've not really thought about that one. I mean, the use of vagal stim with carotid massage or indeed direct vagal stimulation for treating tachy arrhythmias is well known and has been around for a long time. The idea of using cold shock to do what? Resuscitation, cardiac arrest? No, I don't think so. I don't quite fancy trying to convince the cardiologist to do this. You've got somebody in the ambulance dying of a cardiac arrest, and we're wanting to dip them in a large tank of freezing cold water. I don't think I would be recommending that, no. But an interesting idea. Ben sent me a reference to read. I need to read more.
I think it was more for KC.
Oh, it's for Casey. Oh, good. Ben, again, of course, different channelopathies have sudden cardiac death in different circumstances. Diving the pool affects patients. Yes, exactly. So I sort of tried to make that point, but I was realizing I was running out of time on the two different types of channelopathy that generate the different LQTs. And they're certainly triggered by different stimuli. I mean, I guess my argument would be that tachycardia, bradycardia is going to get you one way or another if you've got long QT syndrome. Although the association with swimming seems to be uniquely associated with one particular type of long QT. David Eisner, intrigued by facial immersion experiments. When we did this, we found that QT interval did lag. This hysteresis was over by 40 seconds. I wonder why your QT intervals change more slowly. I don't know. It's a difference between people in Manchester and people in London, I think. Don't know. We've done this a lot of times. Yeah, we've done this a lot of times now, David, and we always get that slow response. I mean, I've read your paper many times, and the sort of hysteresis that was really, and I'm still not convinced it's not simply hysteresis, but if you wait 3 minutes, it still hasn't recovered. If you look at pacing in the catheter lab and look at what happens to monophasic action potential duration in the cath lab, there's a number of papers from John Cam's group and other groups where they change pacing rates in the cath lab. And I know you know this from isolated cell work. You get two phases. You get that first very rapid phase, which happens within a couple of beats, which is the ion channel restitution. And then you get that much slower phase, which appears to be the ion concentration restitution, so sodium changes, etc. I was going to try and do this without mentioning calcium, but I've now mentioned it. So the slow changes in potassium and sodium are probably what account for that change over 3 minutes or so. And in the cath lab, that's exactly what you see. You see a rapid change that happens within a few beats, and then a much slower change. If you look at the amount of change you would expect in 30 seconds in those cath lab experiments, it's something like 40 milliseconds. So it's a big change in the QT interval. Even though it's not complete within that 40 seconds, it takes about 3 minutes. There's something that should happen very fast, and we don't see that. Now, it could be the nature of the stimulus that we're employing, because we are, the diving response, the heart rate is dropping fairly slowly. It's not an instantaneous change. So we're not going to see that rapid change in ion channel restitution. So I still haven't ruled out the possibility that this is just a hysteresis related to the rate of change of these events. But it seems different to everything else. We don't have any other method for slowing the heart rate profoundly. And it is replicated by what we see in isolated hearts, where we can slow the heart rate. So I think it's real, but I agree with you. Nicola Pianca, very interesting talk, thank you. So could it be you finally found experimental evidence of the old grandma advice? Yes. Well, I'm not sure about the lunch thing we thought about. I think the old grandma advice is definitely true. That is, if you have cardiovascular disease, don't go and jump into a freezing cold swimming pool. I mean, that just makes sense. So Ben says yes on triathlete test. Thank you for the talk. Very interesting and informative. Comment on how triathletes could be a healthy choice. Yeah, that's an interesting. Grace Muller asked, are they doing the triathlon in the right order? And it's a very good question. I don't know, because actually it might be worse if you change the order, because you got a lot of hot, sweaty people jumping into freezing cold water. So I don't really know. It's a very good idea. I suspect I suspect the better idea is to convince them not to drink Red Bull before they go and do it. Heinrich Tagmeyer, very thought-provoking. Thank you, Mike. Would you comment on metabolic changes? Alanine and succinate described in diving medal steals. Heinrich, metabolic changes. I did a degree in marine biology many years ago, and I've forgotten it all. The one thing I know from that distant past is that these animals pretty much function anaerobically when they dive. They're not taking a lot of oxygen down with them. They dive anaerobically. They shut off blood flow to their skeletal muscle. They produce a massive lactate production. They have a massive oxygen debt. And they function perfectly when anaerobically. And the argument is that, of course, the only major oxygen-consuming muscle that's left after all of that is the heart. And so rather than shut that down, which might be counterproductive, you slow it down. So the comment on the specifics of metabolism, Heinrich, I would have to ask you that. But yeah, they do, for sure, they shut down their skeletal muscle and become very anaerobic. And of course, the old whalers used to know that, because when they came up to the surface to repay that oxygen debt, they had to spend that time on the surface and got harpooned for their trouble. So yeah, very interesting, Heinrich, but I'm not, as you know only too well, I'm not an expert in metabolism. Emilio Mede, did you observe bradycardia when induced long QTs in rabbits? Yeah, well, we get the bradycardia we get in the rabbits is imposed upon them because we stimulate the vagus. So yes, we get a nice bradycardia. Sean Harding, when the diving mammals go deeper, what is that decreases the heart rate more? Increased cold, or is it effective pressure? Good question. For sure they do. The deeper they dive, the stronger the diving response you get, as indexed by their heart rate. The deeper they dive, the slower their heart rates go. There was some theory that the animals knew how long they would dive when they started their dive. And I think that's largely been discredited. That is, they would dive, and if their heart rate went really low straight away, it's because they thought they were going to dive for longer. But now it seems it's just environmental. So, as you say, cold is a stimulus for this, and pressure may indeed be a stimulus. I suspect, well, I don't know actually. So it's a really good question. It could be either, because of course, inevitably, when they dive deeper, both of those things change. I genuinely don't know the answer, but for sure, the deeper they go, the slower their hearts go.
Or is it just time, Mike?
Time, yes, good point now, we named that. Ben Levine, because high frequency is dependent on ventilation, is a vague on it. Okay, yes, we'll move on from that. Charles Chung, I have limited experience in electrocardiography and autonomic control, but I'm curious if the autonomic conflict could help in explaining the variance from Bazit's equation and improve diagnosis in cardiovascular disease. No, I just think Bazit's is probably just, an approximation. I think, I suspect under steady state conditions, and that's what we care about really to make these measurements. Under steady state conditions, we just need better algorithms for predicting QTC. And Bazit's is a decent algorithm, but lots of people come up with lots of variations. Rosanna, thank you. Hi, Rosanna. Heather Gunn, yes, has answered my question. Richard Heads, triathletes are wearing wetsuits, hot and adrenergic drive or facial immersion. Surely explains the incidence of DWEF is far higher than can be explained by other predisposing factors. Yeah, I think, Richard, you make a good point, is that Mike Tipton's done some studies where you can titrate the amount of cold shock response versus the amount of diving response you get by how much of your body gets exposed and how much of your face gets exposed. And if you titrate one against the other, you can come up with a very nice sweet spot where you get more arrhythmias or fewer arrhythmias. If the cold shock response is really strong, the tachycardia dominates. If the facial immersion is the only thing that happens, the bradycardia dominates. So to get that sweet spot in between where they interfere with each other requires just the right amount of clothing, or the wrong amount of clothing if this is dangerous. And so yes, you're quite right. The amount of whether you're wearing a wetsuit or not influences this. Rosanna, my question is related to that by Crystal Ripplinger. How much the response is dependent on face holding, breath holding? Yeah, okay. I think we sort of answered that. It's driven predominantly by cold and wet, but apnea is an important component of it. So the two big drivers for the diving response are getting this part of your face wet, the trigeminal region of your face, cold and wet, is a strong driver. If you carry on breathing when you do that, you get a much reduced diving response. So the combination of cold and wet on this central portion of your face where the trigeminal nerve innervates with a breath hold is the strongest driver. Apnea causes marked sympathetic activation. This is a standard test. Yeah, agreed. Nicola Pianca, could this autonomic conflict be influenced also by heterogeneity of cardiac innervation? Yeah, I think that's absolutely the key. Something that could happen in pathologies characterized by dysautonomia and diabetes, for example. Yeah, absolutely. I completely agree. I think heterogeneity of innervation is massively important. I saw Sian Harding, and may or may not still be here, but Sian, much more expert on this than I am, but that heterogeneity across, not just between the nodes and the ventricle, but between base and apex, etc., massively influences not just contractility, as Sian has shown many times in things like Takotsubo, but also arrhythmogenesis. So I think heterogeneity is key, which is probably why our naive experiment of simply perfusing autonomic agonists through an isolated heart was just a waste of time, really. It is heterogeneity that's important.
Yeah, Sian is still here, by the way.
Oh, okay. Well, she can't speak, which is ideal. No, thanks, Sian. The related question as to why the Arctic enema obstacle in the Tough Mudder regularly kill people. Richard, I don't think we want to go there. Okay. Begonia, hi Begonia. The experiments that you performed in ex vivo rabbit cells were on healthy rabbits. Have you done or published similar experiments on atherosclerosis? No, we haven't. We have, and I think that's massively relevant. Again, we induced autonomic conflict in a perfectly healthy heart, and it really didn't do very much. It's only when we combined it with long QT syndrome, iatrogenic long QT syndrome, we gave them a drug, that it worked. So yeah, it'd be very interesting to do that. And since I know you've got mice with atherosclerosis, I can tell you we've also got the dual autonomic innervation of the isolated mouse heart has worked. We've had that working before in the past, although James Winter sadly has left science. Amir Fafi.
As well.
I may have missed this, but do you suppose in the underlying mechanism of the autonomic conflict, why do changes in K channel that you mentioned happen? Right. Right. So obviously you've got the changes in the K channel that you're born with that are mutationally driven. Okay. So people who have an inherited long QT syndrome, that's a problem. Okay. The other problem, of course, is changes in the K channel activity that are induced by us taking substances or drugs that influence our potassium channels. And of course, that's the major danger for QT prolongation that is induced by pharmaceutical agents. So that's why the drug companies are so paranoid about making sure that the drugs that they prescribe for your hay fever, whatever, don't prolong your QT interval by blocking potassium channels. So two real reasons. One is you're born with it. The other is you get it by taking drugs that are usually therapeutic, but sometimes not, that prolong the QT interval and block potassium channels. Pete Wilmshurst, Destiny triathletes, what is the role of immersion pulmonary edema? Okay, very good question. I think I would guess, Pete, you're a better person to answer this than me, but most of the deaths in the triathletes occur in the first 200 meters. Okay, so my guess is that at that stage in the process, they have not been in the water long enough to have serious pulmonary edema. I don't know this, but I'm guessing. Okay, as far as I understand it, pulmonary edema is a hydrostatic problem of immersion, which will develop over many minutes, even hours in the water. And since most of the deaths are in the first 200 meters, unless they're particularly slow triathletes, I would have thought they'd have been through that and off within minutes rather than in the time necessary to get pulmonary edema. So my guess is it's probably not related. Probably more important in your patients are people who are divers who've been in the water for a long time.
Right, and should we just go for one more, and then in the interest of time,
do you want to pick one?
Anyone you like. I mean,
Richard, I've definitely not mentioned. Richard Heads is still talking about Arctic enemas. I think we've about exhausted everything, I think. So.
Well, Alicia Mattiazzi as well.
Oh yeah, I didn't see that one. Alicia. Hi, Alicia. I'm trying to relate this autonomic conflict with a different time-dependent adaptation of restitution mechanisms. Can you comment? Increase in sympathetic tone. Yeah, I mean, I think you're absolutely right, and I sort of touched on this with David Eisner's question, in that restitution, mechanical restitution, and indeed changes in heart rate seem to have at least two underlying mechanisms, one with a fast time constant, one with a slow time constant. So the fast time constant one is ion channel restitution, which occurs pretty quickly. I mean, you know as well as I, because you've done many experiments like this, that when you change the heart rate in an isolated prep, within 10 beats or so, the ion channels are back to where their new steady state. The other is the change in ion concentration, so extracellular potassium, intracellular sodium, intracellular calcium load, etc. And I think those are much slower processes. Calcium load probably fairly quickly. Sodium and potassium changes probably a bit slower. I think we've also got my own personal area of interest, which is sympathetic activation of sodium transport. We know that the phosphorylation of the transporter proteins, of phospholemon, of phospholamban, etc., they can occur quite fast, but it takes a while for that to have an impact on, for example, intracellular sodium. Calcium probably reacts a little bit quicker. So all of those factors play into how quickly we come to a new steady state. Some of them will change fast, some of them change much slower. So yes, I think they all play in together in adaptation, and some of them may take a number of minutes to come to a new steady state.
Great. Well, Mike, I think you've been pretty impressive. Probably close to 40 questions. I definitely think you need that water.
I can stay here all day. I quite like this.
Really great talk, and well done to the people that have actually stayed on. I mean, it shows your commitment as well. So this was really...
As my discussion with... I got my excuses in early, and my discussion with Ben Levine will have demonstrated that fundamentally I'm not an integrative human physiologist, or indeed a diving mammal physiologist, but it's too irresistible to give up the chance of studying this because it's so interesting. So I'll see you in Texas, Ben.
And you fell into the David Eisner's trap. You said you're not going to mention calcium, but you did.
Oh, no.
So
Alicia's fault.
So thank you very much, everyone, for listening. We're actually not taking a break for Easter because we're nuts. And so we're back here again tomorrow, and then back again on Monday and Tuesday. But tomorrow's talk I've already announced is Dr. Susmita Sahu from ICANN Sinai, New York. And thanks again. And the video will be available online because Mike has kindly agreed to have it recorded and actually release a lot of the unpublished data as well this way. So thanks again, Mike, and thanks for a wonderful talk.
Pleasure.